On that note, after that attempt at a joke, I'm going to begin now. I just want to welcome you all back to Sussex Universe. So, put your hands up if you've never been to a Sussex Universe lecture before. Okay, that's probably a little bit more than half the people, which is great that we're getting lots of new people coming today. So, Sussex Universe. I'm going to introduce Sussex Universe and I'm going to introduce tonight's speaker. So, Sussex Universe has a history of, I think, more than 10 years, when it really started off as a lecture series led by students in the Department of Physics and Astronomy. Now, this all kind of changed during the COVID pandemic, when this is when Will was actually running this series. He's both an organizer and he's a lecturer tonight. But as the pandemic hit, we decided to do something a little bit different. In addition to moving the series online, we decided to broaden the scope of the series to the other science departments in the university. So at that time, I think there was a great need for people to kind of, continue engaging, continue learning things and not miss out on these events. And we used the pandemic as an actual opportunity to broaden the scope of what we were doing. And that worked really well. We managed to get talks covering a whole wide range of topics. And then, just this time last year, we returned to an in-person format after, I think at that point, it would have been 2.5 years of no in-person lectures. So we're now in our second kind of season of back into in-person talks. And so over this time, these talk series have grown. It's great to see so many people today. We were a little bit anxious that we were going to fill the room up, but you can see that we've pretty much got this perfect. So there are still some spaces, but any more it might be uncomfortable. Okay, so this is our first of the autumn lectures this year. We have a whole series of lectures which are going to be going on every 2 weeks over the coming semester. And they don't just cover physics and astronomy, they cover all of the different science departments from the university. So for example, in 2 weeks' time, we have a psychology lecturer, we have an engineering talk, we have another psychology talk right at the end of the year, and then we have another physics talk. And then next semester, we'll have a whole range of talks as well. Hopefully you all learnt about today from either the online broadcast system for the university, or maybe Facebook, or maybe the mailing list that we still have. We are actually going to try and change the way that we market to people over the next few weeks. For example, consolidating into a mailing list that we can use. But you can always find us on the University of Sussex website. If you look for Sussex Universe on Google, you will end up on our website, and that's going to be one of the best places to look. So I'm done waffling for today, so I'm going to introduce today's speaker, who is Dr. Will Roper. Many people may have noticed, and Will has informed me of this several times, that there was a slight mistake in the programme because Will wasn't advertised with his doctor. Now, the reason for that was because at the time that we actually made this programme, Will wasn't actually a doctor yet. He'd just completed his PhD viva, so this is where you defend your PhD thesis, but he hadn't yet had his corrections signed off, which means, in my eyes at least, that he wasn't actually a doctor.
Very convenient, so that he can pretend he didn't mess up the post.
Possibly. Now, because Will has been so involved with Sussex Universe for pretty much the last 5 or 6 years, is that right? Maybe even longer?
Yeah, a long time.
We also decided to introduce a new format, and so actually Will's lecture today is a little bit of an experiment. And the experiment that we're doing today is we're giving PhD students who have finished, like Will, who have completed, also the opportunity to promote their work to a wider audience. So Will, like all of the PhD students, has spent between 3 and 4 years working on one concentrated research topic, and we think it's a really good idea to allow, now not students, but people in Will's position, people who've completed their PhD, to be able to advertise and celebrate some of the work that they've done. So again, tonight's talk by Will is a test to see how this goes, basically to see if PhD students are any good at giving talks. Well, that bombed, didn't it?
You get a big slap.
Okay, thanks, Will. So I'm very, very pleased and somewhat proud to introduce Will. So me and Will have worked together for many years. So not only has Will been a collaborator on Sussex Universe, but during his PhD I co-supervised Will, and I co-supervise him today as a research fellow. So I think in one tiny little part, some of what Will's going to talk about today has been influenced by myself, but I'm going to pass it over to Will and say, Good luck.
Well, yeah, thank you very much, Steve. So yeah, the sad thing is, if you're on the continent, you do a PhD, you do a public defence of your PhD, and in Finland you're allowed to bring a sword to defend yourself. This is not PhD defence, so you can't come with it. But hopefully, yeah, over the course of this talk, I will hopefully be able to show what I've done in some sort of coherent fashion, or at least that's the goal. So Steve's just done a lovely job of introducing me, but just to put a finer note on it, I am what we call a computational astrophysicist. So I care about space and I care deeply about computers. I'm a developer, which is just my excuse for basically keeping up my coding addiction. So I do it all night long and never sleep. But when I've got my science hat on, I work with Webb. So I work with the first Galaxies, and I'm interested in what I see as the ultimate history of the universe. So for life to exist at all, you need these first galaxies to make the elements to make life. I also thought, given what this talk is meant to be like, I'd go through a bit of my unorthodox history, and I did try and find some photos to base myself in the process, but I couldn't find any. I'm sure my parents have some better ones. But yeah, many years ago, I did music tech and media A-levels, pretty unorthodox for someone with a doctorate in physics. And I also thought I was very cool, as you can see from this wistful photo as I look off into the distance. I think my mother took. But yeah, these are the layabout years. So I didn't do much, I didn't do very well, and I didn't want to do what I was doing. I didn't know what I was doing. And again, because I thought I was really cool, I toured in a band for a while, I tried to make it, I was a walking cliche, I flipped burgers, I worked in kitchens, even worked in a garden centre, and got nowhere. And I got to the end of this 5-year period and watched far too many space documentaries and thought, I know what I'm going to do, I'll do physics. And I applied for the foundation degree here, and I was rejected. So I went away and I did an access course, and my tutor from that access course, Kevin Clark, is actually in the audience, which is a nice sort of full circle. And after that access course, I was allowed onto the foundation degree, and then I did a foundation degree, did a master's degree, did a PhD, and now I'm a research fellow at Sussex. As for what the future will hold, I hope it's not Sussex. But who knows? So I seem to be trapped here. So yeah, back to the actual topic of the talk. So hopefully, by the end of my rambling, you will know the answers to these 4 questions. So why do we run simulations? What makes up a universe? How do we translate that into a computer? And what can we use simulations to learn from? What can we learn from simulations? So I'm going to start with pretty pictures of galaxies. So we point space telescopes, or indeed massive telescopes on the ground out into space. We get back these lovely images of galaxies. We can learn all sorts from them. We can learn about the size distribution of galaxies. We can see areas of star formation. So the dark trails you can see in this image are dust lanes where new stars are forming. And we can also look at collections of galaxies. So you can see galaxies interacting. You can see the huge diversity that exists in galaxies. So just in this one image, you've got what we call spheroids. There's some spiral galaxies. So there's some galaxies that are about to merge. And in this image on the right, you can see what an example of gravitational lensing. So we can learn about the mass distribution of the universe just by looking at a picture. And that's done by taking these galaxies, which are all blurred into straight lines around the central cluster, and that tells us how much mass is inside. Now, these things are beautiful, but as far as I'm concerned, they're a nuisance. They're in the way of what I care about, because I care about the tiny blurry dots you can't even see on this projector. And they look like this. So they're a collection of pixels, decidedly uninteresting to actually look at, but incredibly interesting from a history of the universe standpoint. But there is one. This is sort of the first issue with observations with no theory underpinning them at all. You can't see much. We can't see the structure of these galaxies. We can't learn much about them. And the second problem is every image you look at is a snapshot. So it's just a fixed point in time. We can look back 10 years later, nothing will have changed because galaxies care not for the human lifespan. Yeah, so we need something else to basically unlock the secrets of galaxies. And that's where simulations come in. So in a simulation, we can write models that we think describe the universe. They've got various knobs in them that we can twist and turn and see what happens at the end. But taking a universe that's made incredibly large, incredibly old, and taking all of those constituent parts and putting them into a computer is entirely non-trivial, because everything is horrendously complicated. So that's what I'm going to talk about for the first half of this talk, and then the second half I'll go through some of the work I've actually done, and basically how I lost my mind over the course of 3 years. So this is the general picture that we have of the evolution of the universe. So it starts with inflation, over here on the left-hand side. This is the realm of theoretical physics or conspiracy theories, and I know nothing about it. You tell me what happens there and I just take it as a given. After all of that nonsense is finished, you get recombination. The universe becomes semi-sensible again. You've got atoms having condensed out of the primordial matter and radiation field, and that's produced the cosmic microwave background, which if you're old enough, as some of the people in this room are, to remember, if you've turned on your TV, you used to get static. And that static, some of that was the cosmic microwave background, so this echo of the earliest epoch of the universe. And then there is the wonderfully named cosmological dark ages. So this is a period of the universe after recombination where the sort of hot, very radiation-filled universe is cooled. There's no light, there are no stars. There's just nothing. And then there's the epoch I care about, where the first stars and the first galaxies form. So out of that darkness there is light, in a very prophetic manner. And that is something we're quite uncertain as it stands, even with a couple of years of work there. And then there's the rest of the universe. So I don't care about what happens after that, I'm just going to lump it in. There's lots of interesting things that happen, but I don't study them. This is where we start our simulations. So we let the theorists fire out. They tell us what the universe should look like at a particular age. It deepens the cosmological dark ages, and that's where we start our simulations. So everything prior to that, I now totally ignore. Everything after that is the focus of my work, apart from the rest of the universe. It's just so that's the evolution, but what is the universe actually made of? So the universe basically has 3 main components in it. So there's the biggest component, dark energy. It drives the expansion of the universe. I'm going to mention it once and once only. I do not care about it. It enters our cosmological calculations in the back of the simulation. We don't do much more with it other than that. Then the next biggest contributor is dark matter. So dark matter is this mysterious form of matter that we do not understand, hence why it's called dark, same as dark energy. But we know we need it. It controls, it interacts only under gravity, and as I will show you in a bit, it controls most of the structures we see in the universe. And then there's visible matter, or baryons, which is everything else. It's the stars, it's me, you, the planet, the chair you're sat on, the planet we're stood on. It's everything else, and it's only 5% of what actually makes up the universe. So we really don't understand a lot in the grand scheme of things. The next thing we need, after actually reading into the universe, is we need the fundamental laws that control it. So first and simplest, we've got gravity. First discovered by Newton, refined by Einstein. In my work, I don't touch Einstein's equations, they are wonderful. I nearly went into work on them, but then I stayed at Sussex and I did not. There is also electromagnetism, of course. We need to work out how light interacts. We need electromagnetic fields. And on much smaller scales, there's the strong and weak nuclear forces which hold atoms together and control fundamental particles. And those we can ignore straight away, because we're never going to be working with the scales, we're never at the scales where we can resolve what they do. So I looked this up earlier on, just so I had the number in my head, and it was way bigger than I thought. My body is made of 10 to the 27 atoms, so a billion atoms. And I don't think you could even hope to complete a calculation, no matter how clever you were with the biggest supercomputer we currently have, using that many elements. So forget those straight away. And I'm also going to skate over magnetic fields, because I contend that anyone that tells you they understand magnetic fields, or at least astrophysical magnetic fields, is talking nonsense. So I'll start with gravity, and I think it is the most important thing. And that starts with the n-body problem. So if I were to set out 25 particles, mass elements, something I need to calculate the forces between them. It's just 25, it's not many. I'd have to calculate the force between every single pair of particles up here. And that, once you add it up, is 625 interactions. I'd have to sit there and write out. But what I can do, and what we do in simulations, is I can collect them together. They're already mass elements, let's just make them bigger mass elements. And that lowers my resolution, but it means that the calculation is much, much smaller. So now instead of 625 interactions, I need to do 16. Now, 625, 16, they're basically an order of magnitude to an astronomer. But when you get to really, really big numbers, this really, really matters. And the first person to actually use this principle didn't use a computer at all. This is one of my favourite things to talk about. The first n-body simulation was run with light bulbs in 1941 by a guy called Holmberg. And he took a bunch of light bulbs, set them up as two interacting galaxies, and then moved each light bulb based on the amount of light it was receiving, and calculated the acceleration due to gravity based on that. And through doing this, he was able to show the formation of spiral arms in a galaxy just using a handful of light bulbs, which, I personally think is pretty incredible. Just in 1941, we already had a way of describing how spiral arms form, and yet we're still going. Of course, later on, in the 1960s, a guy called Lindblad came along and ran on the Swedish BESC supercomputer, which is the supercomputer you can see on the top of this slide. The same set of simulations, but actually using a computer. And because it was in a computer, later a movie was made. So this is that set of simulations. It's not the two interacting galaxies, it's just one. But effectively, these rings are part of the spiral, the disk of the galaxy. They disturb them ever so slightly, as you saw with those arrows, and then they let it evolve. So it starts turning. And you can see the particles clustering up, they're shifting, the attraction between the different rings is changing, and eventually you'll see the formation of spiral arms. So there you go. Just the outer ring's been torn apart by the gravitational forces and created spiral arms. You'll see in a second 4 spiral arms very briefly form. So that was then. That was the 60s. Now our supercomputers don't look like they did. In fact, my watch, I've got a picture of a laptop, but I actually worked out my watch is significantly more powerful than a supercomputer was, so I could run that simulation on my wrist, which I think is kind of nice. But our supercomputers actually look like this now. So they don't normally glow blue. This was Intel demanding that the CPUs they paid for were advertised in their colour. But yeah, so it's these huge racks with cables going everywhere, and the amount of computation there in comparison is just astronomical. And the lucky thing is that n-body problem I just described is exactly what we need to describe dark matter. Dark matter interacts only gravitationally, therefore it is an n-body problem. And with that supercomputer, I ran this simulation, so you can see the expansion of the universe in this one. And you can see the formation of filamentary structures and dark matter halos, so between these filaments are nodes where mass is collecting. And as the universe expands, as it ages, this mass collapses into the universe's skeleton. It is controlling potential worlds in which all matter will form. And these problems are relatively easy to solve with computers. I mean, to the point where we have so many different ways of solving gravity now, and everyone thinks their way is much better than everyone else. And of course, mine's the best. But yeah, so we've come a long way, is my sort of way of saying. And if you didn't believe the simulation, well, we can look at observations. This is the Sloan Digital Sky Survey map. So on the radius of this circle is distance from us, effectively, and you can see, clear as day, if you plot the galaxies that we've seen in that survey onto this map, you can see the filamentary structure of the universe. So we're not talking nonsense, it's there, and it's actually the sort of original proof for our cosmological model, the lambda CDM. Next is visible matter. So visible matter is the bane of my existence. It takes all my lovely codes, which run really, really fast, and makes them messy and slow and just a nightmare to work out. So baryons are, as I said earlier, everything else. They're everything that we see. They're luminous matter. And the nasty thing about those is, instead of just acting gravitationally, which they do also, they also interact with each other. They enrich each other, they impart energy onto each other, and they have a bunch of complex things which I'll go into over the course of the next few slides. So the majority of baryons are actually a bit simpler than that, so they're just gas. We can treat it as an ideal gas law. which means it behaves as a fluid. It has pressure, it has temperature, it has phases, and it has a chemical composition. So all we need to do to solve the evolution of this matter is solve fluid equations, which they are complicated. They're significantly more complicated than the equation of motion for gravity, but they're not too bad. But we need a method for solving this. So one method, and the one that I favour most, is you use particles to represent your fluid. Other people use meshes, which is actually the image I've used there. And this is just a standard hydrodynamical test we have. So it's just a fluid, a gas. You've got two densities of gas, and one is moving past the other. And you get these little eddies called Kelvin-Helmholtz instabilities. And you can see them in the real world. So in clouds are a denser form of the atmosphere, and as they pass the less dense atmosphere above, the same processes happen. So it's happening on Earth, it's happening at massive scales in the universe. You can also take a bunch of your collaborators and turn them into a hydrodynamical simulation. So I pay particular attention to Steve. Yeah, this is now my standard way of introducing my collaborators. But again, this is literally, it's ridiculous, but this is all just those principles. So I've represented the image as the particles, then I'm evolving them using the fluid equation. And I've got a bit of an addiction for doing this now, it's a bit of a problem. So yeah, that's gas, nice and simple. Now things get really messy. So stars, again, like I talked about earlier with mass elements, we can't hope to simulate all the stars in the galaxy. The Milky Way alone has 100 billion of them, if not more. And that's just infeasible to run a simulation that big. It's just an impossibility. People do, when they're focusing on a single galaxy, you can do that. But I personally don't care about singular galaxies. I want hundreds of thousands or millions of them to get statistics out. So we have to treat them as if they're below the resolution of our simulation. So we have to find a way of encoding the fact that stars form from dense clouds of gas that cool down enough to fragment and then produce a certain mass of stars. We do this with what's called a subgrid model. So there's tons of subgrid models out there. They all think they're the best, and they all have different ways of dealing with this issue. So we just write down a set of equations which we think describes how a certain particle at a certain resolution should form stars, and we make stars. But if we do just run that, we end up with far, far too many stars. It's because we've forgotten the fundamental thing about stars, that's that they die. So the really, really young, short-lived, bright stars will burn out really quickly, and they'll go supernova and blast energy and chemicals out into the universe. So this energy just heats its environment. So what we needed to form stars was cold gas, and what a star's death does is heat up that gas. So this is like a symbiotic and a parallel process that regulates each other. So we have to include models for this as well. We have to say, okay, we form this mass of stars. It's going to produce this massive energy, this amount of energy, and kick it out into the universe around it. And when we do that, we can then get the right amount of stars being formed. And this is just, I've lost the credit for this video, but it's too good not to show. So if anyone knows who made it, please don't comment. On the left-hand side of the slide, you can see just light. So you can see dust lanes, you can see the disruption of the spiral arms of the galaxy. And on the right is temperature. So you can see all these little bubbles popping up, the really, really small bubbles, and that's just star formation happening. So the stars are forming, and then 10 million years later, the younger ones are dying, exploding. So it can be quite a violent process. And then the final ingredient we have is probably the least understood, and that's supermassive black holes. So we call them active galactic nuclei, AGN. So I might intersperse that into my talking. But AGN are even more complicated, partially just because we don't understand their formation very well. So to accurately model black holes, we need a way of putting them into the simulation in the first place, and we need a way of modelling the energy that gets kicked out. So the way we actually put them into the simulation in almost all cases is, in my opinion, the worst thing to do. And if we say that thing's big, that should have a black hole, and we put one in. And I think it's probably one of the biggest issues we have in modelling at the moment, but we don't know what to do better. So yeah, I hope to fix that at some point. Probably won't be me, but I still hope so. Yeah, and then just sort of like we'll be talking about the first galaxies, and black holes, they're massive things that collect lots of mass, so you might think, oh well, they're not a big deal at high redshift at the earliest times. And I've just included this image to sort of debunk that. This is 1 billion years after the Big Bang, this temperature image of the universe. And those massive outflows you can see are a really, really massive AGN that is kicking out tons of energy along its poles into the universe because it is formed really, really early and established itself as sort of a force of nature. The other really important thing that we need black holes to do is further regulate star formation. So when we get towards later times in the universe, the rest of the universe section, you need a certain number of galaxies to stop forming stars. They need to die and become passive to match what we see in the universe. And what we think does this is black holes, because again, they get to a certain mass, they get really angry, kick loads of energy out into the universe, and basically starve their galaxy of gas. So they can't form stars anymore. That's it. Here's just a video of AGN action, so you can see what's happening is the black hole, I keep saying AGN, the black hole in the middle is accreting mass, and as it accretes that mass, it superheats it to a plasma, and some of that energy needs to go somewhere. And it goes somewhere along the poles of the rotation of the black hole. And that's what you can see in these massive bursts that are coming out of this black hole in this movie. So yeah, that's sort of the very high level of what we need to simulate the universe. So it's all of these separate processes. We need some initial conditions, so we need some dark matter, maybe some stars and gas if we're starting our simulation late, and some black holes, and then we chuck that all into a supercomputer and we get simulations out. They can be massive in scale with really low resolution, so we're only looking at the cosmic web and the interactions of matter at that scale, or they can be much, much more much better resolved, much lower resolution, much higher resolution, much lower mass. And we can look at the actual demographics of galaxies and their evolution and untangle that. And that's roughly what I did. So this is just a video of bringing it all together. So the colour you can see in the background is gas density, and then the overlaid on that are the stars, so the light, you can see white stuff. And this is just a video of a pretty small volume of the universe that I simulated. And that focused on the biggest galaxy that formed in that box, which you can see over the course of the universe eats its surroundings. So it's accreting lots more gas from the coloured bit and also just chewing away at the galaxies that are forming around it. And so something like this would have happened with our Milky Way, and in fact I think this galaxy is about the same mass as our Milky Way. But because we've run a simulation, we're not tied to just looking at mass distributions or light distributions like we would in an image. I can plot anything. So this is the temperature of the universe. So this is just the temperature of the gas from that previous video that you can see in the top corner, and you can see the black hole in the center of that galaxy has superheated the surroundings around it by the late universe. And so just to give you an idea of scale, you can see the bubble at the end. So our galaxy is what, like 10 kiloparsecs in size? Just a number, 10 kiloparsecs. The actual bubble blown by this galaxy is nearly 8 megaparsecs, so it's 1,000 times larger than that on the side. So these processes are extremely violent. And that comes to the end of my section on how we do a simulation, and I hope what I now say from this point on will make sense. And I'm keeping miraculously to time. I gave this variation of this talk to Bright Astro, and it went for an hour and 15 minutes, so fuck a week. But yeah, so this is the workflow of research and simulation, or at least the way I see it. So we need some initial conditions, that's what I talked about, so what the theorists tell us the universe should look like. We take our cosmological model into account there. And then we need a simulation code that does the gravity, it brings together the gravity, hydrodynamics, and subgrid physics. So all that star formation, the black hole modeling, everything like that. The code that I use for that is Swift. So I'm an active developer on it. If you want to use it, you can. You can just Google Swift simulation code, you can download it yourself. You won't get it working. I tried this recently and it didn't go particularly well. I'm working on a way of getting it nicely packaged up for people to use. But you can see it, it's all publicly available. Yeah, and I mean, I think it's great, but yeah. So then you need a subgrid model. So I use the Eagle subgrid model, or indeed its successor, which will be called Calibre, but it's not out yet. So this is sort of my justification for the title of the talk. It was the title of my thesis, The Tale of Birds and Bug Fixers. I think it confused people, no end. But yeah, and then what your simulation code gives you at the end is it just gives you a sea of particles. So we don't know, we can't point and go, that's a galaxy, right, from that. It's just a bunch of particles with their positions, their velocities, all these properties. But what we want a galaxy. So you need a structure finding code. I've written one of those called Mega. Sadly not a bird, although John did point out to me when I was giving this talk somewhere else, there is the mega bird that was around a sort of prehistoric bird. So I'm taking it. I'm running with it. And then you perform your analysis. So we can count how many galaxies you get at a particular mass. You can look at the relation between the mass of a halo and the stars that are in it. You can, as I'll talk about more in a minute, look at the size of galaxies versus how bright they are. Or you can go hog and actually model the what a galaxy would look like for a particular telescope. So these are all very high redshift, so again, they're blocking very openly. Or you can go slightly insane for a short period of time, like I did, and show that if you made the universe entirely out of cows, the initial Webb observation claims to have broken the universe and made the universe question our cosmological model are consistent with the universe made of cows. Just to point out, those findings have all been debunked. It is nonsense, but yeah, I still want a universe made of cows. So yeah, brings me on to, I'm going to talk about some of my research I actually did. So this research I actually ran for the length of my PhD, from the first month of my PhD to the end. It was a very deep rabbit hole, as I'll try and convey to you now. And I think this is a very apt title for it. So it just was panic from start to finish. But yeah, so my main work focuses on a simulation suite called flares. So there's another sort of simulation we run called a zoom simulation, where you focus your simulation in a particular region of the universe, simulate that with the resolution you want, and then degrade the resolution everywhere else just to make it cheaper. And this flares is made up of these 40 zoom simulations, so these spheres you can see dancing here. And the important thing is they cover a range of environments. So from the top left-hand corner, there's lots of stars. So it's a very dense environment, down to the bottom right-hand corner where there are very few stars. It's not just the ball. Yeah, and we can use it for all sorts of wonderful things. We've published, 16 papers from it now, or something like that. It's been quite successful. But what I did from it was look at the size of the galaxy. So this is what we expect. This is you'll see a few of these. So on the y-axis is the size of a galaxy, how big a galaxy is, and on the x-axis is how massive it is, how its massive stars. And it should behave as you expect. Something gets more massive, it gets bigger. That makes sense, just fundamentally. But 1 month into my PhD, I was presented with this. And I'm sure it shouldn't escape your attention that this is exactly the opposite. As something gets more massive, it gets smaller. So we panicked for ages. Wondered, oh no, is this wrong? Is everything with the simulation wrong? Does it work for the first galaxies at high redshift? So the first question we wanted to ask, well, this is mass. We looked at the size in terms of mass, but what the observers measure is light. So let's look at the light. And you can ignore most of this, just focus on the bottom panel of this plot. You can, this is taking the size of galaxies as measured from their light and plotting it against their light on the x-axis. And you see now this isn't negative, it's positive. So, and this scatter you can see, so these diamonds, the pluses, they're Hubble observations, and they agree. So everything is fine. When you look at the galaxies the same way an observer would, we get the right answer. Now, this is an extremely troubling answer to get if you're doing a PhD, because it means the rabbit hole is deeper. It means that you can't just walk away from it and say, well, that's wrong. There is much more to describe. So, and I think at this point, I just need to do a quick aside to make sure this makes sense going forward. Measuring the size of a galaxy is a bit of a weird thing. So you might just assume, oh, we go out to the edge of that galaxy and that's how big it is. But the edge of a galaxy is pretty poorly defined. Galaxies are weird shaped. So even this fairly simple galaxy is an oval. So how do you measure the size of an oval? So what we do instead is we define a radius called the half-light radius, or mass, if you're talking about mass, half-mass radius. And that is, you sum up all of the light you see from a galaxy, and you find the radius that encloses half of it. So for this image, it'll be something like this, and that's what we call the size of the galaxy. That's a way we can consistently talk to each other about how big a galaxy is. Now, the different thing that happens in the high redshift universe is everything's much more compact. All the star formation is really, really compact. And that means that you're enriching a very localized area of the universe. You're kicking out chemicals into it, which aids star formation, but the other thing they do is produce what we call dust. And dust gets in the way of light. It absorbs it, it re-emits it, it scatters it, and it stops us from seeing. So it's basically in the way of observers. It's a problem that we have to deal with. But because everything's so compact at high redshift, you effectively get something like this that's happening at low redshift. The central portions of the galaxy are super attenuated. They're basically covered in this opaque cloud of dust. And if you took this galaxy and now measured its half light radius, you'd actually measure something like this. So that's what's going on in this plot. We've gone from looking at mass, we get something negatively sloped, because we can see all the mass. But when we look using light, there's a bunch of light we cannot see that's heavily obscured, which leads to us measuring a larger size that's consistent with the observers. So the negative size mass relation, so that things, as they get more massive, they get smaller, could be physical, it could be real, what's actually happening in the high redshift universe. But again, that causes the rabbit hole to get deeper. So fine, we have an explanation, it makes physical sense. But why? Why is it negatively sloped? What's causing this shape? What's the actual physical process going on underneath? So to do that, I took my code mega, and we can make what we call merger graphs. So every line on this family tree is a generation of halos in our simulations, and then we connect them together into a family tree, so we can trace the evolution of these halos. By doing that, I can trace the evolution of galaxies across the size mass plane. So the in this one, the pinky bluey coloured points are earlier, and the later points are darker. They're red. So we now have this picture where galaxies are starting out, they're diffuse, they're big, they're not very massive, they're low mass, and they're very diffuse and cloudy, amorphous shapes. But then something happens that causes them to jump right to higher masses and also down in size. And it turns out, I'm not going to present the plots because I'm confused my own collaborators. But what's happening here is you get this diffuse sort of blobby system that forms enough stars to start enriching the gas around it. And one particular region will collect together enough chemicals to start cooling efficiently, and then a runaway will happen. It will start collapsing, it will start forming stars, which will make more enrichment, which will allow the collapse to happen more. And in this really localized area, you end up with lost stellar mass form very quickly, which is what this jump is that you can see from the big things down to the high mass compact things. So fine, the rabbit hole's open. We've explained it. We've got like a physical mechanism that causes this to happen. We've seen that it's consistent with observation. It's what we want. But there's one question that I didn't answer, and that's how the hell do we go from there to there? And that was sort of painful to work out because we stop our simulations 1 billion years into the universe. And it turns out it's actually really simple what the explanation is. So if you look at the temperature movie here again, you can see that this hot bubble around this galaxy is blowing out, heating a lot of gas around that galaxy. It's not that the galaxy is in isolation, this little compact thing made of various bits of matter. It's embedded in this much bigger cloud. And you can see, the huge bubble there, blue. And that gas is bound to the halo, it's part of it, it's part of the same entity. So what you have at high redshift is you have a really compact stellar distribution, and this is to scale, surrounded by a gas reservoir that's 100 times bigger than the galaxy. But it's doing nothing, because that core is so dense and compact, it's holding on to everything there. It's holding on to the energy, it's holding on to the chemicals, and it just can't make it out and enrich and help star formation in the extended gas distribution. And you can go and measure that. So here on the x-axis, you've got the radius of the galaxy, and then the amount of star formation on the y-axis. And you can see, and then the yellowy colours are early. So in fact, it starts at 500 mega years, so 500 million years after the Big Bang, down to sort of about 10 billion years after the Big Bang in the sort of purpley colours. And what this very simple plot shows is there's a peak of star formation at a very small radius at high redshift, which shifts to the right. And it's basically, what you can see there is that extended gas distribution turning on. There is a point at which the big core cannot hold on to its enrichment anymore. It's blasted out into the surrounding area, and star formation begins, and we perceive this increase in size of the massive objects. And that's sort of the end of my insanity. So miraculously, I'm actually finishing entirely on time, which might be a first ever for me. But yeah, so this was 3 years of insanity condensed into about 15 minutes. There were a lot of weird offshoots from this, lots of rabbit holes that didn't go anywhere. But this fits the picture, and no one has disproved it yet. It's very hard to actually look at the telescopes, so I think that's the secret to theoretical work. You do something that someone can't ever look at, and then it's forever possible. But yeah, thank you very much.
Thank you very much, Will. Congratulations on keeping to time. That was great. So assuming that Will is happy, we have a bit of time for people to ask questions. So I will try and check. Do we have any questions from the audience? Over here?
You see gas density. Is it always the colours like that?
But computational astrophysicists have a horrible case of like, this is this colour. So dark matter is purple, even though it's not, it doesn't interact with light, but we always cover it purple. Yeah, we always use the same colour maps and stuff.
I think we should make a change and we should use completely different colour maps just to confuse our readers. Question right there at the back?
So you had that family tree.
Mm-hmm.
What were the fluctuations in it?
Which one specifically? The shifts?
Specifically the point-like fluctuations.
So that's nothing interesting, I'm afraid. It's the way this is done is this is just the x coordinate in the simulation relative to some central halo, and that central halo changed definition at our early time, which meant that you've got x minus y, but y changed. I'm afraid it's really boring. I should have fixed it.
So another question there at the back?
I was interested when you said at the start that the size of the body was 10 to the power 27. Was it molecules?
Oh, in the body, yes.
And then it's interesting that that's basically the same size of the observable universe.
Yeah,
In terms of, was it centimeters or meters, right? 10 to the power 27 meters, I believe.
yeah. You got to test my recall.
It
Yeah.
made me think, like, you use, when looking at the structure of the universe, you use the body as a reference point, and say, for example, some of your simulations, they kind of looked like simulations of looking at like neurons in the brain. Do you kind of use the body? Do you think that can be used to, or do you use it to work out the structure?
I don't personally. Funny that you've just brought back to my memory that there was a group that simulated cosmological volumes with bacteria. That's the closest thing I can think of. But they actually, I forget how they did it. They set their initial conditions out with a particular protein on the petri dish and then they evolved. And I'm not sure it was useful, but it was interesting. There's a lot, but there is a lot of this. Like, the universe does look like neurons on the larger scales, and there's a lot of this sort of, what's the word? I can't think of the word. It's gone. But yeah, there is a lot of
Coincidences?
That's not the word I was searching for, but it was twice.
Anthropomorphism?
It's something like that, yeah. But, yeah.
Any more? Question right here in the middle?
If black holes keep absorbing matter, surely at some point there's not going to be anything left in the universe, or at least it's going to be very, very dark.
Yeah, so that's one of the death scenarios of the universe, which is always fun to discuss. There is one death scenario of the universe where just all, if it doesn't expand so far that nothing interacts, which is the heat death of the universe, it could all just be eaten up and eventually just spiral into a single black hole. I think given our cosmological model, it's incredibly unlikely, but yeah, could. This is not a question mark, but my favourite way the universe could die is there's the Higgs field, so all that stuff from the LHC and the Higgs particle that gives everything mass. That field is in an unstable equilibrium, or at least we think it is. So if that equilibrium shifts somewhere in the universe, like anywhere, it could be beyond where we can see, that bubble would expand faster than the speed of light, redefining mass and tearing apart atoms at the base level. And we never know it was coming, so at any point that could happen.
So what Will meant there is the one that might keep you awake at night. One of my colleagues from a few years ago, she actually wrote an entire book about this. I'll try and remember what it was called, but yeah, there's an entire book on this idea, which I am never ever going to read. Any more questions for Will? Are they in the middle?
It's an energy question, an energy scale question. So, in the 1950s, when they detonated the hydrogen bomb, the most powerful thing that we've ever managed to detonate, because there's a certain similarity to the revealers as well. What kind of scales are we talking about in comparison to something that we've actually done? What kind of orders of magnitude, perhaps, or beyond that even? What would you say?
Do you know what's a joule to an erg?
This is a difficult one. So
It's the H-bomb. The H-bomb.
the H-bomb that we've used, they convert, I think, about 10 grams of matter directly into energy. About 10 grams. Now, the number that I know off the top of my head is that for a supermassive black hole, right, supermassive black holes will every year, when they're turned on, convert about half the mass of the sun into energy.
Ah.
Okay, so these are vastly different scales that we're talking about here. And supernova, which I think is one of the things that you were showing in the videos, that's what some of the things that you were seeing as the gas was heated up. They're kind of comparable to a supermassive black hole, but on a relatively short period of time. So we are talking, 10 to the 20 kind of more, or even more, maybe 20 to 30 times more energy in some of these cosmological events compared to what we're doing on the Earth. So we're not doing very much here on the Earth, as destructive as we are.
So it would be in the order of hyper objects, and some of this, beyond normal understanding, just as a main thing that's what scale.
Yeah.
Any more questions? Or you got there first.
Hi. May I ask, did you make a simulation based on a real galaxy? And can you name it? And what is the results? I mean, what is the impact of your research to science in astrology?
So, I do not simulate actual galaxies. There are people that do. Well, actually, I suppose I kind of do now. I work with people that simulate actual galaxies, and we're obviously very interested in the Milky Way. So there's this whole field called constrained simulations, where we run millions of simulations to try and find the Milky Way. And then we'll find that set of simulations that led to the Milky Way and do it again and again and again to pin it on its evolution. The impact of my simulations. My work has had some impact on people that care about what I do. But it's a problem. It's a problem with astrophysics in general. Like, how do I impact society in any way? I can make you pretty pictures, and I can inform you of what your money has paid me to do. But I can't do much more.
At the risk of answering Will's question, Will's question.
You're going to anyway, go ahead.
I am. So I think one of the things that Will has spent a lot of the last 2 years working on is a way of making some of our computer codes much more efficient, much faster. So if anything, one of the impacts that Will's work is going to have is that it's going to reduce our use of resources. So one of the problems with our field, with this field, is that we have to run these simulations on supercomputers. Supercomputers use an enormous amount of energy. One of the payoffs of Will spending 2 years kind of working on this code to optimize it is that we're going to be able to do this with smaller impacts in the future. So it's about kind of increasing the sustainability of the field, which is really, really important for us because we are an energy-intensive field. And so Will's work, I'm sure, will have a whole load of academic impact, but it is going to make our field, in that small way, that little bit more sustainable.
Thank you.
I may have been outside when you mentioned some of that, so I apologise.
I didn't actually.
Okay.
No. So if you want to talk about energy, but this is energy use. So we're moving into what we call the exascale era now. Buzzword. But that means that simulations that actually reach that benchmark will use the same amount of energy per second as a fairly sizable town. And we have run simulations that do use that are that size. So there is this huge consideration. We really do need to be using codes that are more efficient. I know the code that I work on, if you sort of try and work out the increase over something from 10 years ago, it's something like 300 times more efficient, but that's still not good enough. And then there's hardware that we have to take into account as well. So these HPCs are cooled with active water cooling. So there's pumps that are pumping water around 500 computers plus. So yeah, it's incredibly important. So I do nothing for society, and I'm destroying the environment.
Maybe in the future we should only run supercomputer simulations in the winter and pipe that water into student accommodation.
Sussex needs a swimming pool.
Will, you stole that idea from me. I've been complaining about this.
Actually, that is true. He says this all the time. That's the only time it's ever been true.
Any more questions for Will? Right there in the middle?
You said about very dense galaxies and stuff, right?
Yes. Yeah.
Why do they not just collapse into black holes?
Because they're held up by there's orbital motions. So they're really compact, but they're stable in their motion is one thing. But you also do have there's radiation pressure. So there are things pushing out as well as just keeping it stable. They're holding it together. So I said we don't know how black holes form. One of the ideas for how black holes form is very, very early on. Gas does runaway collapse, and it cannot stay stable and hold itself up, and it does just form a direct collapse black hole. So yeah, it does happen. The scales, once you get into a galaxy, hold itself together.
I think time for one or two more questions if there are any. Up front.
How accurate are the simulations that we have nowadays compared to, the real thing?
Mine? I think we do pretty well with certain things, right? So it depends what you're looking at. So I don't know that I actually have it. Okay, here's I think the only example of a research paper with observation plotted on it. This is halo mass, stellar mass on the y-axis, and there's a bunch of scatter in the observations. There are observational biases, but we get the right answer effectively in that, and that we see that in all the relations. I mean, I showed the size mass one. The scatter technically agrees. So we do know to a certain extent we are getting the right answer, but things that we don't know. So there are weird extremes that we can't model properly. There are certain processes we know we're leaving out, so we know there's a fudge. So with all the simulations I work on, we don't deal with light. There are simulations that use a thing called radiative transfer, which kicks photons out into the universe at random angles, and it traces their paths, imparting energy as it goes. That is obviously what truly happens in the universe, but we have to fudge it, because otherwise our simulation is not going to finish. So simulate, we're never trying to simulate, if the universe were a simulation we existed in, we're not trying to do that yet. We're just trying to use simulations as a tool to probe something we're interested in.
I think time for one last question. You've got there first.
Okay, I know this sounds a bit stupid because I'm not a physics student. The first question is about there are 5%. You said the visual, is it called visual matter?
The visible matter, yeah.
Visible matters. Are they equivalent to all the rest of the 95% of the dark matters?
Equivalent in what sense?
information from?
So
Are they balanced or just maybe?
no. So I think that this is one of the this is our model of the universe. This is how we understand it currently. But I think what's most interesting about what we do know is that we only know 5%. We can only see 5%, and we only have accurate models for 5% of what makes up the universe. So I was a bit disingenuous when I was putting that plot up and saying, because that is specifically the percentage of the energy density of the universe, which is the amount of energy there is in the universe is made up of this stuff. If you go down to just matter and forget energy, it's 85% is dark, 25% is visible, or barrier.
In a visual way?
Yeah.
Okay.
So, yeah, we know very well. And it's not balanced.
And when you start out the simulation, what is the original force or something to push the simulation? Because otherwise it should be fixed, right?
Oh, it's all gravity. So the structure of the simulation is we have that start point, and then we take steps, and each step is a particular like dt. It's like 1 second. It's much longer than for argument's sake, 1 second. We calculate what the motion should be based on gravity, if the baryon thermal stuff, and then work out its new position. Then we do the next step, and then we do the next step, and sort of tens of thousands of those steps make up the universe.
Okay.
Yeah, that was probably a bit much.
So it's 7 o'clock now, so we should just thank Will again. Do you mind just putting the files on? So as you can see, our next talk will be in 2 weeks' time by Dr. Faith Batcham, who is one of our psychologists, and she's going to be talking about something completely different, which is digital sensing in nature progression. So as I said, we're going to have a whole series of talks this semester covering all areas of science, and all of these should be accessible to a wider audience, so I hope you all do come and join us. And I'm sure Will hang around for a few more minutes if anyone has any final burning questions for Will. And thank you all again for coming. I hope you had a good time.